Welcome back, everyone. Today I'm going to show you how Python creates a linked list. Specifically, this video will show you a singular linked list. Initially, the list we're going to build looks like this. The way the code works is over here on the left. In order to build a linked list, you must first have a series of nodes. So you first create a class, which we'll call node. This class will only have an initialization method, and each node will consist of two components. The first one is called data. That's the data that's being stored in the node. And the second is called next. This will either point to the next node or contain the keyword none. When I say point to the next node, that means what is stored in the next field is the address in memory of the next node in the list. So as you can see in this diagram I have on the right, the first node will have a data field of 1, and its next field will point, that's what the arrow means, to the second node, which has a 2 as its data field. And the second node will point to the third node. The third node will have a 3 in its data field, and this will be the end of the list, so its next field will be set to none. Now, of course, you can make the list as big as you want. What makes a linked list different from just a list in Python is that the nodes are not in consecutive memory locations. In a list, which is the same as an array, all the elements are in consecutive memory locations. But in a linked list, as you see here, the nodes can be anywhere in memory. They don't have to be right together. That's why it's important to have a next field that will contain the address of the next node in the list. When I say it contains the next node in the list, that means it points to the next node. Okay, let's look at the code. So you have a node class. Then we will create a linked list class. Now, the linked list class is not inheriting the node class. These are two separate classes. Here in the linked list class, we're going to have two things initialized in the initialization method. The first is going to be something called head. This will represent the start of the list. This head pointer will always point to the start of the list, always point to the first node. Now, the size attribute is going to be just an integer telling us how many nodes we have in the list. This is a carryover from the way the book did linked lists. You don't necessarily have to have one of these in there all the time, but I'll keep one in just because it's consistent with the textbook. In this linked list class, I've defined three methods. The first one is called append. And as you can see by the comment here, the append method adds a node to the end of the list. It'll be the last one in the list. So first thing you do is you create a new node by calling the node class's constructor or initialization. And of course, we have a parameter value being passed into this append method. So that value will get sent to the node's initialization method to create the node. Now we need to put it at the end of the list, but we're doing one check beforehand. If head is equal to none, meaning the head is not pointing to anything, that means we have an empty list. So that means in that case, we're putting the first node into the list. So we will say self head is new node. Else, meaning if head is not none, that means we have nodes in the list. We're going to add it to the end of the list. So I'm going to create another pointer named temp and set it equal to head. And now I'm going to use a while loop to move temp to the end of the list. As you can see, the while loop says while temp.next is not none. This is a very common phrase we use to see if we're at the end of the list or not. If temp.next, if the next field of temp is not none, well, that means we're not at the end of the list yet. So move to the next node. What you're doing here, this line, temp equals temp.next, that will move temp from one node to the next node. And so eventually when the loop ends, the while loop ends here, when temp next is equal to none, then we set the next field of temp equal to the new node, and that will add it to the end of the list. We also increase the size by 1. The append method is how you add a node to the end of the list. So for example, we create a node that has 1 in it, and we say none. Here's the node. Okay. Here's head. Head points to this. All right. Let's assume we've added that node. So first, head was null. Oh, head was none. So in that case, head points to new node. This line does this. That creates the node. Now then, suppose we make a second node with the value 2 in it. So I'll make a second node, put a 2 here, and this also has none in its next field. A bit better. There, good enough. Okay, now what happens is, in this case, we come to the else because head's next field is no longer none. I should do one more thing. Well, okay. Head is not none, so we have something in the list. So what we're going to do is now we create another pointer named temp. Here's temp. That points to the same node that head points to. That's what temp self equals head is going to do this. It's going to make temp point to the same node that head points to. While temp next is not none, temp equals temp not next. Well, it turns out temp's next field is none, so we don't go in the loop, but then we do this. Temp's next field is equal to new node. Well, temp points to this node, and so its next field will no longer be none. It's going to point here. So that's what happens there. Now suppose we create one more node. It's 3. And its next field is none. All right. So we start the else clause again, set temp equal to head. It's pointing to the same node that head does. Now it says while temp dot next is not none. Well, here's temp. The node it points to, its next field is not none. So guess what? We do temp equal temp dot next. Actually. So here's what we're going to do. That means temp no longer points there. Temp is now going to point to this node. It moved. Temp equal temp dot next meant temp no longer points to the node with 1. It moved to the next one. It points to the node with 2. And now the while clause, while temp dot next is not none, well, it is none, so the loop stops. So that means temp dot next is new node. So that means the next field of the node that temp is pointing to, that means the 2, it now points here. There you've got a list with 3 elements in it. I'll leave that up there for a bit. Forgive my lack of penmanship with this thing. Okay. Let me erase some of this. The other method I have here is called insert at front. Again, we create a new node, but we're going to insert the node right at the front. So once again, we see if head is none, meaning there's no nodes in the list, then head becomes this new node. Head points to that new node. Else, we do have nodes in the list. Here's what we're going to do. New node dot next is head. Okay? So what's happening here, I'll erase temp because we're not using it now. So here's our list. Now suppose we create another node and say it has a 4 in it, and it has none. Better looking 4. Okay, so here, what we say is new node.next is head. So that means the next field of this brand new node we made is going to point to the same node head does. So that means this none goes away, and this goes here. It's pointing to that node. Okay, it's pointing to the node with the 1. And then finally, we're going to say self head is new node. Well, guess what? This is the new node with the 4. So that means head no longer points to the node with the 1. It points to the node with the 4. That's the new beginning of the list. Okay. And finally, we have a method named printList. So here we say if the size is 0, we could also say if self head is none, print list is empty. Else, we're going to go each node individually and print it. So here comes temp again. Warning, I'm about to draw something. This is temp. Temp points to the start of the node. Temp is set equal to head. Print that. While temp is not none. Okay, so while temp is not none, you could also just say while temp if you wanted to. But while temp is not none is a little more descriptive. Okay. So we're going to say print temp data. That means you print the 4. And then we do temp equal temp dot next. That means temp moves to the next node. Here, prints the 1. Then it moves to the 2, prints the 2, etc., and so forth. Here we have the main program. Now, first, I'm just going to append a 1, 2, 3. And I'll show you what that looks like. When I run this program, okay, when I first print the list, I get the list is empty. There's nothing in there. I just created the linked list, an object of the linked list class. So after I create the object, there's no nodes in the list. So I print the list, it's empty. But then I say linked list append. I do 1, 2, and 3. And here's what I get. I get 1, 2, 3. Now, next thing I'm going to do is uncomment these lines right here. Now I'm going to insert a 4, a 5, a 6 at the front. Notice I'm calling the insert at front method, and then I print the list again. So if I run this again, as you can see, there's my first print of the list, but then I call the insert at front method 3 times, and look what I get there. I inserted 4, 5, 6 at the front. That means when I call it the first time, 4 gets put in the front of the list. Call it the second time, 5's at the front of the list. Call it the third time, 6 is at the front of the list. And here's what I get. 6, 5, 4, 1, 2, 3. The first call where I added 1, 2, 3, I was appending, adding to the end of the list. So that's why you see the numbers in order, 1, 2, 3. But for 4, 5, and 6, I was adding those numbers in that order to the front of the list. They're each being put in as the first node. And that's why they're in reverse order. That's why 6, when I'm all done, is at the front of my list. This is your introduction to singularly linked lists in Python. If you have any questions, please send me an email at kmuldrow at lbcc.edu.